This is a revision summary of the AQA A-level Chemistry topic of the reactions of ions in aqueous solutions. You might find this video useful as kind of pre-reading before you start studying this topic, or as a summary before an end of topic test or your final exams. If you are revising for the final exams, it's worth pointing out that although this is a separate topic to 3.2.5 transition metals, most of the metals described in this video are transition metals too. So that's probably a better place to start your revision if you haven't already revised that topic. In order to discuss the reaction of ions and aqueous solutions, you need to be comfortable with all of these definitions, which we've met earlier in paper 1. The first specification point in this section is about different coloured complex ions that form when certain metal compounds dissolve in water. They're all these octahedral hexa-aqua ions with 6 water ligands surrounding the central metal ion, so all you really have to remember is the charges and the colours. We have the bright blue copper 2+ hexa-aqua ion that you see in copper sulfate, the green hexa-aqua ion 2+ ions, then there's a colourless hexa-aqua aluminium 3+ ion, and also the hexa-aqua ion for iron 3+. You've met that as a sort of orangey brown rusty coloured substance, but also under certain circumstances it can also form its monohydrate type, and then it's a sort of pale lilac-y violet colour. The specification includes examples of complex ions that are 3+ and 2+, because they want you to have this idea that the 3+ ions like aluminium and iron 3 have a greater acidity than the 2+ ions like copper and iron 2. The reason for this is because those 3+ ions have a greater charge and therefore a greater charge density. This means that they have greater polarising power. So they attract the water molecules more strongly, and in doing so they weaken the OH bond in the water molecule so that it breaks more easily. When that happens, 3 hydrogen ions are released, which are responsible for the acidity. In terms of reactions, all the specification says at this point is that you need to be able to describe and explain the simple test tube reactions of M2+ and M3+ ions with the bases hydroxide and ammonia and carbonate. If we think firstly about the addition of hydroxide, this is the same reaction that you met at GCSE if you took triple science. If you add sodium hydroxide to a source of copper 2+ ions, then you're going to see a blue precipitate. If it's iron 2+, then we see a dark green precipitate. If iron 3+, then we see an orangey brown precipitate. And if we have a source of aluminium ions, then it forms a white precipitate, which will redissolve if you continue adding sodium hydroxide. If you add limited ammonia, you get the exact same reaction, not just something that looks the same, but literally the same chemical reaction. This is because the ammonia acts as a Bronsted-Lowry base. It joins up with the hydrogen ions from the water to make ammonium ions, leaving behind a surplus of hydroxide ions, which then behave in exactly the same way. To make this slightly more complicated than GCSE, we now write symbol equations with state symbols. For hexa-aqua copper 2+ or hexa-aqua iron 2+, one of the 6 water ligands is replaced by a hydroxide ion. Then another hydroxide ion does another bit of substitution, and we're left with this solid precipitation. This is a partial or incomplete substitution. You're not going to see all of the water molecules being replaced. We can summarise this by joining together the 2 steps to make a single equation. Alternatively, ammonia will take 2 hydrogen ions away from 2 of these 6 water molecules, and what we're left with is that same precipitate alongside 2 ammonium ions. Aluminium is the interesting one of these ions, because if we take those aluminium ions and add a source of hydroxide ions, then we get this white precipitate that you can see here. But if you keep on adding hydroxide ions, then eventually the white precipitate redissolves, and it makes a colourless solution instead. The hydroxide also reacts with acids. If we have a source of hydrogen ions, then we can turn it back into that hexa-aqua aluminium ion that we had at the very beginning. Since aluminium hydroxide reacts with both acids and alkalis, we call it amphoteric. So limited ammonia will break apart some water and leave us with this incomplete substitution where 2 of the water ligands are replaced by hydroxide ions, and we get an overall uncharged precipitate. But if we continue to add excess ammonia, then a further substitution will take place. 4 ammonia molecules replace the 2 hydroxide ions and also 2 of the water molecules. So what we're left with is a different incomplete substitution. The 2 water molecules are as far apart from each other as they can be, and then also the 4 ammonia molecules make up this tetraamine diaqua copper 2 complex ion. This is accompanied by quite a vibrant colour change to this really dark, deep blue solution. Next on the list of test tube reactions is the reaction of 2+ ions with soluble carbonates like sodium carbonate or sodium hydrogen carbonate. In each instance, rather than forming a complex ion with 6 water ligands, the metal ion joins with the carbonate anion and the 6 water molecules are kicked out and left over. This leads a precipitate to form. The reactions of the 3+ ions are slightly more complicated than the reactions of the 2+ ions, but it helps if you remember that the 3+ ions behave more like acids due to their greater polarising power because of the higher charge. If you think about how an acid would react with a carbonate, you know it makes a salt and carbon dioxide and water, and that's exactly what's happening. So if we've got some aluminium hexaaqua ions, to start with they have these 6 water molecules, and 3 of those water ligands are going to dissociate to make hydroxide ions and hydrogen ions that can then go on and join up with some of the oxygen from the carbonate ions to produce some carbon dioxide and also some water. So what we observe is a little bit of effervescence and then also the precipitate. For aluminium this is going to be a white precipitate, and for iron 3+, it's a sort of orangey rusty brown precipitate. Thank you very much for watching, and I hope that you're now feeling a bit more prepared for any upcoming assessments that cover this topic. Good luck for the exam, and if you did find this useful, don't forget to like and subscribe for more A-level chemistry content coming soon.